that should be 0. So it ends up being 7 minus 0.06 over 7. The other terms, these two, end up canceling out in this case. Right? Now, if you have time, it's a good idea to take the point you're given and plug that into a function directly. And certainly that value should be close to what you get here. Questions about this one? Okay. I'm going to keep the topics on this board just so we have a list to keep referring to. So we're good here? All right. Okay, next we'll do a chain rule one. Let's do our 11.5, number 5. So given function z, function of xy, x squared plus xy plus y squared. We're going to change a variable. X is s plus t, and y is equal to s times t. And you're asked to find partial z with respect to s, partial z with respect to t. All right. So the idea is that partial of z with respect to s, write it this way, with respect to s, partial of z with respect to t. So notice we have only one function, scalar value function z, with respect to two variables. So I list of variables in differentiating with respect to in different columns. So this is going to be, by a chain rule, equal to partial of z with respect to x, partial of z with respect to y, times the Jacobian matrix of change of variable, the partials of x and y with respect to s and t. So we're going to put partial of x with respect to s and y, s and t rather, and partial of y with respect to s, partial of y with respect to t. Right, so this is what the chain rule is saying, but then if we multiply all this out, which involves taking the dot product of this row with this column, that gives you dz ds, and then you get dot product of this row with this column to give you dz dy. So in other words, dz ds is going to be dz dx, dx ds. Notice the x's, you can say they cancel in a sense. Dz dy, dy ds. And dz dt is dz dx, dx dt, plus dz dy, dy dt. So if you want dz ds, you have to make sure that you get to s through all of your old variables. So you need to take x into account and y into account. Same thing for computing partial of z with respect to t. So here it's written in matrix vector form, here it's all multiplied out. So these two are saying the same thing. So now we can go ahead and compute all these things. So zx is going to be 2x plus y. Zy is going to be 2y plus x. But now what we need to do, before we can actually apply these over here, we need to write these in terms of s and t. So we're going to have 2x is equal to s plus t and plus st. And here we're going to have 2st plus s plus t. So now, because ultimately, because we want the partial with respect to s and t, your answer has to be in terms of s and t. So we can fill these in here, 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 and here, but we still need the partials of x and y with respect to s and t. So xs is 1, xt is 1, ys is t, yt is s. So now we have all the partial derivatives we need, we can go ahead and plug in. So we're going to have 2s plus 2t plus st dx ds, which is 1, plus 2st plus s plus t dy ds, which is t. So that's the end of that part. dz dt is zx times dx dt, which is 1, plus zy 2st plus s plus t times dy dt, which is s. And that's it. Okay. Questions on where maybe given a function of x and y or a function of x and y and z, where those variables are now become functions of only one parameter, t. So in this case, you would only have a single column here, but it would only be one derivative to compute. But the idea is going to be the same. All right. Okay. I'm going to skip directional derivative. Straightforward. I will definitely do a Lagrange multiplier. Let me spend time on a local max-min saddle point one. Or
yeah, I think that's part of that.
okay. 0.7, number 7. All right. So we have the function f of x, y. 1 plus xy. X plus y. Okay, so finding max, min, or saddle points. Okay. Now, in this case, well, might as well multiply it all out. So that's going to be x plus y plus x squared y plus xy squared. So now we'll compute the gradient. So we have partial with respect to x, that's going to be 1 plus 2xy plus y squared. The partial